you examine the neighborhood of this node, and you associate the nodes in the neighborhood, and now you're almost done. Meaning you can now go through the neighborhood of this one and associate that node, and so forth. So in essence, you start with a very, very rough set of nodes that you know are the same, and then you improve your mapping step by step. And you end up with something that could be qualified as an intersection operator between binaries, meaning it tells you what is the same between those two. By implication, it tells you also what is different between those two, and that has been of great use and lots of fun in the vulnerability analysis business. Now the question is, what do you do with an intersection operator? For malware analysis and classification, you want something like a similarity measure, but strictly speaking, you have something more powerful. An intersection operator is a lot more expressive. And we had to build ourselves some sort of similarity measure from the intersection operator, because, well, we are not very good at stuff like generating family trees, so we couldn't really come up with an algorithm on how to create family trees from intersections. And we wanted to steal the ideas of the bioinformatics crowd, and they operate on similarities. So how do you build yourself a similarity measure from an intersection? That is not totally trivial in the sense of, well, the obvious idea clearly is you take just the size of the intersection divided by the size of one executable. That might be a possibility. But the trouble here is that you might have contains relationships. So in this case, it's relatively clear that we have this intersection here, and that has a relative size relative to the whole executable, so you can estimate what the similarity would be. But we have differences in sizes, and we have differences in how much these two executables overlap. So we have essentially not a symmetry here. How similar are these two? I don't know, well, even these two. Now if you consider the intersection here, the intersection is equal to the size of the small executable. So for the small executable is 100% similar to the bigger one, but the bigger one is not 100% similar to the smaller one. So because we really couldn't get a clear idea on how to do this, we just invented something that half works and that is really stupid. The idea is that you calculate these similarities or this intersection on the call graph level, on the function level, and on the instruction level. And then you have essentially, well, you divide these values by the size of the executable as a whole, and then you have 3 similarities for each executable. And you just average them, and then you get 3 values of similarity, and then you average that with a given weight, giving more weight to the call graph than to the instructions, and you're done. And it's a very, very experimental physics style work, which means, well, this might work. So it's really not exact at that point. The advantage is that if you have an infinitely large executable and an infinitely small one, which is completely contained in the big one, you still get 50% similarity, whether you want it or not. Okay, so the other thing is scalability. We had to come up with a way of running our algorithm in essentially linear time, which we've managed to do, which is good. The algorithm in the end runs in about O(n) times m, where m is the average size of an executable, in functions, which is usually less than 1,000. That is a very approximate version of the algorithm. We then, after running an approximate version of the algorithm, run a more detailed analysis on those samples that were deemed interesting by the first run. So we really have a very approximate similarity, and then we take the most similar ones and run a detailed analysis. And the other way of making this thing perform better is discarding clones. A lot of executables will not actually be changed a lot, in the sense of, you will see, well, the AV industry will tell you that they see a gazillion new samples a day. Usually they kick around numbers like 60,000 unique samples a week or something like this. And they actually believe that these are unique programs. And somebody is not making the calculation that in order for there to exist 60,000 new pieces of malware a week, we would have to have several countries doing nothing else. And those wouldn't be small countries, right? So you know in advance that most of the samples you'll see will be minor, and when I say minor, I mean minor variants of other executables. So what we do is, we just keep the most relevant ones. You send in 25 samples, and when a new sample comes in, and it is extremely close to an old one, you just discard it. And only if it is similar to an old one, but sufficiently different to warrant being kept as a new specimen, you keep it. So that's the entire idea. So the result is that what's eating our computing time now is the emulation and the unpacking. It's not really the classification. All right. Entire system has been parallelized except the classification. And this is what the architecture looks like. So you have an XML RPC server up on the front, and a SQL database from which into which it dumps the samples and from which it retrieves the results. And then you have a bunch of unpacking subsystems which fetch executables from the database, unpack them, drop the results back in. You have a disassembly and an analysis subsystem which disassembles and extracts the flow graphs. And then you have a classification subsystem, and those really operate independently from each other. All right. And now I'll show a little bit about what the system does. Okay, so this is the working list of the system while it's running. We're dropping files in there from a German students group called MW Collect, or a German project by Georg Wicharski. They're collecting malware, and we're taking, we've been supplied the malware by them, and we drop them into our classification system, and it gets classified there. And yeah, so what do we have here? We have a bunch of executables, and we have family trees that we can generate from these executables. And they look a little bit ugly because a lot of the samples that we get from MW Collect are very, very similar to each other. So you get many nigh clones, almost exact clones of one executable that have different hashes, but their similarity was somewhere clearly above 95%. So you have ugly executable hash here, and you have a ton of clones here. And in order to make the graph more clear, we can just hide all the clones, and the entire picture becomes a lot more clear. And then we see that we're dealing with actually a much more manageable number of real variants, and even these variants are comparatively similar. This number here indicates the percentage similarity between the samples. So you have these two samples here, and they are 89% similar, so they were just dissimilar enough to not be classified as a clone, and so forth. But all these are just hashes. I've uploaded a few samples that you might know. We've uploaded a bunch of stormworms, and they've been classified nicely together, which was quite surprising to us. Yeah, this system is a lot of fun. Also, we had a really, really interesting incident where, let me flip over, a customer found, had a crash dump with some code from kernel memory in it, and we then investigated and found this driver on his hard disk, which wasn't supposed to be there. And we uploaded the driver to the system as well, and it was, interestingly enough, it had a very small but significant similarity of like 20% or 15% to some bot sample that we had seen. And that was a little bit strange. Why would a driver have a similarity to a bot? And so the first thing we thought was our system must be flawed. So we downloaded the IDBs, like the system produces disassembly files for IDA that you can download, so you upload the executable, and then after it's unpacked and disassembled, you can download the IDB. So we download the IDB and ran bindiff on it, and what's causing the similarity is, amongst other things, this function here. And when we see all these red lines here, that means that the instructions changed quite a bit, but the actual flow graph looks remarkably similar. So let's have a look at the instructions. For example, at this basic block. Now, for those of you that do read assembly, what do you see? Somebody was inserting. Yeah, essentially, it's the same code. So somebody's just inserting garbage into existing code streams. Well, this pushes a value on the stack. It overrides, like it pushes a register on the stack, it overrides the register, and then it restores the register again. So somebody's just automatically going through his code, and whenever he has like 2 or 3 instructions in a row, is inserting do-nothing garbage. And that was quite surprising, and it was nice that we caught it, and I'm quite happy about it. Yeah, so that was this. Back to the slides. so this is what we're doing now. Where is this entire classification game headed? Predictions are usually really, really difficult, so don't call me on these things in a few years. You can easily attack the system, but I think 5 minutes. Okay. You can easily attack the system, but I think you might have to change your build environment quite a bit for it. Let's imagine a future where you don't have self-modifying code anymore. In the long run, I think what will happen is that Microsoft will outlaw self-modifying code. So what will they do then? How can they continue obfuscating that code in the future? And in essence, I see two avenues that they'll be pursuing. The one is insertion of,
They'll just keep writing more code.
That might be true. All right. So one of the things that I think will happen in the sense of obfuscation is insertion of opaque predicates, which means inserting a lot of conditions that are false, but it's not easily discernible whether they're true or false. I'll explain that in a minute. And the other thing that we're seeing a lot are emulating packers, where they take an entire executable, transform it into an intermediate language, and then emulate that intermediate language instead of actually running the code, which is somewhat annoying. Takes time to take apart. So opaque predicates. Well, clearly if you wanted to attack this, you would want your flow graphs to be dissimilar on every new rebuild. So for this, what you could do is you could insert a lot of unconditional jumps. That's what they are already doing in order to confuse people. Unconditional jumps are being optimized away when we generate the flow graph, so we don't really care about them. In order for them to do something clever, they would have to insert conditional jumps, but in a way that it is not evident that these jumps are true or false. Because you don't want somebody else to just run an optimizer on the code and have all the conditions that you built just drop away. Thing is that there's academic research into opaque predicates. The trouble is that all things that they've come up with so far are number theoretic. So you can do something like, hey, we have an opaque predicate here, you can't tell which way this branch will go. You just have to do a modular exponentiation a few times. And clearly it's not an option to add a modular exponentiation into 25 places in your function and still have the program run in reasonable time. Yeah, so that's one thing. The other thing is emulating packers. They're really annoying. And the one thing that we are trying to work on at the moment is at least looking at the public implementations that exist and generating disassemblers for the intermediate language, and then just comparing the flow graphs generated from the intermediate language to the flow graphs generated from another intermediate, like from another run of the same program, or of another mutation of that program, because the flow graphs remain mostly the same. We've diffed CommWarrior on ARM, and CommWarrior and ARM thumb, like CommWarrior A and CommWarrior B, are compiled for essentially different instruction sets. And the structure of the program stays largely the same, so I think when we can extract that stuff, we should be fine as well. Yeah, that's pretty much it. If you have questions or anything, ask them now. If you want to send us malware to classify, you can drop them in a passworded zip file with password infected to vxclass.submit@zynamex.com. We will most likely, I don't give any guarantees of this getting back to you in reasonable time, because it's really just, if you drop us malware and we happen to have spare cycles on our computers, we'll run the classification. There's no guarantee that you'll get an answer, but I'll promise you we'll try to run the system at least once a week on customer submitted or people submitted stuff. All right, any questions? Come on, Dave. Oh, sorry. Actually, the question was back there, I think. Sorry.
I just wonder about the algorithm you were talking about. Doesn't it cause you a lot of problems if executable has been packed with some sort of cryptor that is publicly available on the web? Because if you have several variants of different bots that could be crypted with one packer, you get the similarities for the packer and not for the bot itself.
Well, the similarities for the packers will occur in the calculation if you do it naively. But we already filter out, like the other problem that you have is statically linked libraries from compilers. So before we actually calculate the similarity, we filter out code that we've seen, which means we have a library of code that